Today I'm going to take you through the 6-step process for hypothesis testing. And so we're just going to run through an example doing all 6 of these steps. So our example starts with researchers wish to test the efficacy of a program intended to reduce the length of labor in childbirth. The accepted mean labor time in the birth of a first child is 15.3 hours. Okay, so I'm already going to want to start thinking about that first step and start picking out all the numbers that I'm given and assigning them to the right variable. And this is going to make it a lot easier when I have to start plugging things into formulas. So that 15.3, that is the population mean. And if I keep going, the mean length of the labors of 13 first-time mothers. So I'm doing a sample of 13. So my sample size is 13. In a pilot program was 12.7 hours. There's my sample mean, X bar, and standard deviation, 3.1 hours. So S is 3.1. Assuming a normal distribution of labor times, test at the 10% level of significance, there's my alpha, whether the mean labor time for all women following this program is less than 15.3 hours. So I've got alpha, and one thing I'm going to need later, which I might not realize this yet if I'm working on this problem, but I am going to need the degrees of freedom, which is going to be 1 less than the sample size. So 13 minus 1 gives me degrees of freedom of 12. So I've pulled all the information out of this problem that I need. Now I want to state my hypothesis statements. It's really easy to want to skip this step, but it's crucial to getting the right answer in that final step. So if I go back to that last sentence, it tells me that I want to test the claim that the program is less than 15.3 hours. So less than is an inequality without an or equals in there, which means this will be the alternative hypothesis. And then my null hypothesis is always going to be an equals to. So we're talking about a mean here. So it's going to be mu equals 15.3 for the null, and mu is less than 15.3 for the alternative. And because that last statement, that is our claim, what they're asking us to test. So I'm going to go ahead and label that as well. It makes it easier to make that final decision in the end. And now I'm ready to go on to step 3. State the test to be used and verify the requirements needed to perform the test. So we're doing a mean, and we have a sample standard deviation, which means I'm going to be doing a t-test for the mean. Other ones that we'll look at in this chapter would be a z-test for a proportion is the other one. And I also need to verify the requirements needed for this test. And there are 2 options to meet the requirements. Either the sample size needs to be at least 30, which if I look, we only have 13, so we don't fit that one. So the other requirement that we can meet to make this test work is that the population is normally distributed. And that last sentence tells us, well, we can assume a normal distribution. And so I'm just going to state that here. Population is normally distributed. So now I know I meet the requirements, and I can keep going with this test. Step 4, I'm ready to compute the standardized test statistic and plot it on the sketch here. So I need a formula. Okay, we said we're doing a t-test, so I need the formula for a t-score. And there it is, x bar minus mu divided by s over the square root of n. This is where that first step comes in handy because I identified all of those values at the beginning, and now I just need to plug them in. So if I plug everything into the formula, it looks like this. And now I need to be able to calculate this correctly in my calculator or in Excel. So I'm going to do this in a calculator. It is pretty much exactly the same in Excel. So I want the subtraction to be calculated first in the numerator before I divide. And same thing in the denominator. I need that division to happen before the top and bottom are divided. So I'm going to start with parentheses. And we have 12.7 minus 15.3, close the parentheses, divided by, and then I need more parentheses to ensure the bottom gets divided first. And that standard deviation was 3.1 divided by, and then I need a square root. So second, there's my little square root right there, of 13. Okay, and then I'm going to arrow to the right out of that, and then close off the parentheses. The only difference in Excel is I have to use the function sqrt for square root in there, and I'll show you that in a minute. And so I get a t-score of about -3.02. So I'm going to take that back over here to my problem and add it to my sketch. And the alternative hypothesis was mu less than 15.3, which makes this a left-tailed test. And so I want the area to the left of that t-score. When I go to find it, my p-value is going to be that area over there. If this had been, if the alternative had been greater than, then this would have been a right tail, and I would have wanted everything to the right of -3.02. If it was two-tailed, so it was not equal to in that alternative hypothesis, then I would also add a t-score of +3.02 on the right side, and I would want the area to the left of -3.02 and the area to the right of +3.02. So we're looking at a little bit simpler example. I just need the area to the left of this t-score. So I'm ready to go on to the fifth step. We're almost to the end. So to get that p-value, again, there's some functions in my calculator. They're going to help me out with this, or in Excel. So if I'm doing this in a calculator, I'm going to use the tcdf function on my distribution list in the calculator. And I'm going to be plugging in a lower value, an upper value, and the degrees of freedom. So let's switch over and do that. So second distribution, and there's my tcdf, number 6. Now mine is auto-filling a negative, really large value here, a really tiny value, I should say. And so I'm going to leave that. If it was blank for you, just put in -10,000, and that usually works. And then I've got my upper value is the t-score, -3.02, and my degrees of freedom was 12. So I'm just going to go through this and hit enter. And now all I've got to do is hit enter one more time to calculate it. And oh, I have an error. So I'm going to choose go to. It's going to take me to where the problem is. And it's that here, when I typed this in, I used a subtraction key instead of a negative. So I'm going to switch that to a negative. Happens to all of us once in a while. And then hit enter. And there's my p-value, 0.0053. Again, if this was a right tail test, I would then go 1 minus this to get the p-value. If it was two-tailed, I would multiply this by 2 to get the p-value. Okay, so that's for calculator. If I'm using Excel, it's a little bit different. I'm using t.dist in my calculator. So let's give that a try. So here it is all set up in Excel. I have all my values here. There's my t-score, so I can see right here by calling cells how I calculated that. And now I am ready to calculate my p-value. Always start with an equal, and t.dist, I'm going to just grab it off of this list. The x value that they want here is your t-score, not x bar. Tempting to do, but that's not it. The degrees of freedom, which I got right there. And these are always going to be cumulative, so true. And I get the same p-value here, about 0.0053 if I round that off. Oop. Okay, so I'm going to take my p-value and compare it to that 10% level of significance. And well, this is smaller than the 10% level of significance that I have. So now I'm ready to go to the last step where I can draw all my conclusions based on this right here. Okay, so P was less than alpha, which means that I'm going to reject H naught, the null hypothesis. And now we have to remember, was the claim the null hypothesis or the alternative? So I go back to that second step, and well, ours was the alternative. So that means there is enough evidence to support our claim because we rejected the null. And so I'm just going to tie that back in with what the claim said. So there is enough evidence to support the claim that the mean labor time for women following this program is less than 15.3. And that's it.